Welcome to this walkthrough of LeetCode problem number 2005, Subtree Removal Game with Fibonacci Tree. In this video, we will explore the problem's requirements, analyze the Fibonacci tree structure, and discuss strategies to solve this. Let's dive in. To solve problem number 2005, we first need to understand the structure of the Fibonacci tree and the rules of this two-player game. The Fibonacci tree is a special type of binary tree where the number of nodes in each level corresponds to Fibonacci numbers, and the goal of the game is for players to take turns removing subtrees to maximize their scores. The challenge lies in determining the optimal strategy for both players. One approach we considered is the brute force method. This involves simulating all possible moves for both players recursively, calculating the resulting scores for each subtree removal. While this method provides a clear understanding of every possible game state, it becomes computationally infeasible for larger Fibonacci trees because of its exponential time complexity. Next, we analyzed a dynamic programming, or top-down, approach. Here, we use memoization to store results of previously computed states, reducing redundant calculations. Each state is represented as a tuple that includes the current subtree and the player's turn. This method is much more efficient, with a time complexity of O(n), as each state is computed only once, making it a significant improvement over brute force. However, the dynamic programming approach does come with its own challenges. It requires careful design of the DP states and transitions to account for the alternating turns of the two players. Another method we considered is a greedy strategy, which is simpler but less optimal. In this approach, the player always removes the largest subtree available on their turn, assuming this maximizes their immediate score. While this strategy is computationally efficient, requiring O(n) per move to evaluate the largest subtree, it is suboptimal in the long run. This is because it focuses only on local optimization and doesn't account for how current moves might impact future game states. As a result, players using the greedy approach may miss opportunities to set up stronger positions for later turns, leading to lower overall scores in competitive scenarios. While simpler strategies like this can work in smaller or less complex games, they are not well suited for the nuanced structure of the Fibonacci tree and the strategic depth of this problem. Ultimately, we chose to implement the dynamic programming approach as our solution. The Fibonacci tree's recursive structure lends itself naturally to breaking the problem into smaller subproblems, which can then be solved efficiently using memoization. Each move splits the tree into smaller independent subtrees, making it possible to calculate the optimal score for each state recursively. The key insight here is that the recursive definition of Fibonacci numbers aligns perfectly with the dynamic programming paradigm. This realization allowed us to design a solution that is both efficient and optimal. Compared to the alternatives, the brute force approach was simply too slow due to its exponential complexity, and the greedy strategy, while faster, often led to suboptimal outcomes. Dynamic programming strikes the right balance, offering significant improvements in time complexity while ensuring the best possible results for both players. Of course, this approach does require additional memory for storing intermediate states and careful management of game states, but the benefits of reducing the time complexity to O(n) far outweigh these trade-offs. With this approach, the solution is not only computationally efficient but also scalable to large Fibonacci trees, making it the ideal choice for this problem. In this problem, we're working with a Fibonacci tree, which is a recursive binary tree structure. The Fibonacci tree is defined such that f(0) and f(1) are single nodes, while f(n) is constructed by taking a root node and attaching f(n)(1) as the left child and f(n)(2) as the right child. This structure grows exponentially with n, resulting in a significant increase in nodes as n increases. For instance, f(4) consists of 12 nodes. The problem involves a two-player game where players alternate turns to remove subtrees. When a player removes a subtree, they earn points equal to the number of nodes in that subtree. The game continues until all nodes are removed, and the goal is to maximize the difference in scores between the two players. Understanding the recursive structure of the Fibonacci tree is key, as the larger left subtree often presents better scoring opportunities in the game. To solve this problem, we use a recursive dynamic programming approach with memoization. The core idea is to calculate the maximum score difference for the current player at each node. We define DP node is underscore player 1 to represent the maximum score difference achievable if the current player starts their turn at the given node. The base case is straightforward. If the node is null, the score difference is 0. For each node, we first calculate the size of the subtree rooted at that node. Then we simulate the two possible moves, removing the left subtree or the right subtree. Removing the left subtree adds its size to the current player's score, and we recursively calculate the opponent's score for the remaining tree. The same logic applies when removing the right subtree. The player chooses the move that maximizes their score difference. Memoization ensures that we don't recompute results for the same subproblem, significantly improving efficiency. Special cases, like when the tree consists of only one node, must also be handled appropriately. When dealing with larger Fibonacci trees, recursion depth can become an issue due to the tree's exponential growth. In such cases, optimizing the solution with an iterative dynamic programming approach may be necessary. The recursive nature of the Fibonacci tree aligns well with dynamic programming because solving the problem for smaller subtrees directly contributes to solving the larger problem. Key insights include leveraging the asymmetry of the Fibonacci tree. Since the left subtree is always larger or equal in size to the right subtree, it often provides better scoring opportunities. Using memoization reduces redundant calculations, transforming the recursive solution into a top-down dynamic programming approach. The time complexity of the algorithm is proportional to the number of nodes in the tree, making it efficient when paired with memoization. To represent the tree, we use a treenode class, where each node points to its left and right children. Additionally, a dictionary serves as the memoization table to store results for each node, _player1 pair, avoiding redundant computations. The algorithm's time complexity is proportional to the total number of nodes in the Fibonacci tree, which grows as the nth Fibonacci number, fn. The space complexity mainly comes from the recursion stack and the memoization table, both of which also scale with the number of nodes. To implement the solution, we start by defining the Fibonacci tree structure using a recursive function. Base cases for f0 and f1 return single nodes. For larger n, we recursively construct the left and right subtrees and attach them to a new root node. The subtree_size function computes the total size of any subtree by recursively summing the sizes of its left and right children along with the root. The dynamic programming function dp calculates the maximum score difference for a given node and player using memoization. If a result for the current state is already in the memo table, it's reused to avoid redundant computation. This setup ensures that the algorithm efficiently handles all subproblems. Within the dp function, we begin by calculating the sizes of the left and right subtrees of the current node. The two main options are to remove either the left or the right subtree. When removing the left subtree, the size of that subtree is added to the current player's score, and the opponent's turn is simulated for the remaining tree. The same procedure applies for removing the right subtree. The current player then chooses the option that maximizes their score difference. If the current player is player 1, they aim to maximize the difference, while player 2 aims to minimize it. This is implemented by taking the maximum or minimum of the two options, depending on the current player. The result is stored in the memoization table to avoid redundant calculations in future calls. Finally, we can use this function to solve the game for any Fibonacci tree. For example, building a Fibonacci tree of order 4 and starting the game with player 1 allows us to calculate the optimal score difference using the dp function. Here, we start by importing the ru_cache decorator from the functools module to optimize our recursive calculations. The first function, fib_tree_size, computes the total number of nodes in a Fibonacci tree of order n. This is a straightforward recursive function, where the base cases return 1 for orders 0 and 1, and for higher orders, it sums the sizes of the two smaller Fibonacci trees and adds 1 for the current node. Next, we define a class solution containing the main method findWinner, which determines the winner of the subtree removal game. The method accepts two inputs, n, the order of the Fibonacci tree, and x, the node where the game starts. Inside this method, we introduce another recursive function, subtree_size, which uses memoization to efficiently calculate the sizes of subtrees. This function is similar to fib_tree_size but leverages ru_cache to store intermediate results, significantly improving performance. Finally, we calculate the size of the entire Fibonacci tree of order n using subtree_size. Here, we proceed by initializing the scores for both players, Alice and Bob, as 0. Additionally, we create a visited list to keep track of which nodes have been explored. The size of this list is total_size plus 1, where total_size is the number of nodes in the Fibonacci tree. This ensures that each node is visited only once during the simulation. Next, we define a recursive function DFS, which simulates the game. The function takes two arguments, order, representing the current node, and player, indicating whose turn it is. Inside DFS, we first check if the current node has already been visited. If it has, we return immediately to avoid revisiting and duplicating work. Otherwise, we mark the node as visited and update the score for the current player. If the player is Alice, her score is increment, while for Bob, his score increases. After updating the scores, the function explores the left and right subtrees recursively. These correspond to the two smaller Fibonacci trees, and the turn alternates between the players as the recursion proceeds. When exploring the subtrees, the recursion is performed only if the order of the current node is greater than 1, ensuring that we stay within the valid bounds of the Fibonacci sequence. The DFS function is called recursively for order 1 and order 2, with the player alternating between Alice and Bob on each call. Once the recursive traversal is set up, the game begins by invoking DFS with the starting node X and Alice as the initial player. As the game progresses, each player accumulates points based on the nodes they visit, and the visited array ensures that no node is counted more than once. Finally, after all nodes are processed, the winner is determined by comparing the scores of Alice and Bob. If Alice's score is greater than Bob's, she is declared the winner, otherwise, Bob wins. The method then returns the name of the winner as the result of the game. Here, we start by importing the necessary Java utilities and defining our solution class. The first method we create is FibTreeSize, which calculates the size of the Fibonacci tree for a given order n. The size of the tree is derived using the Fibonacci sequence, where each node has a left and right subtree corresponding to the sizes of n1 and n2, plus the current node itself. For the base cases, when n is 0 or 1, the size is 1 since these represent the smallest possible trees. Then, we define the main method findWinner that will determine the winner of the game. We prepare a memoization map to store subtree sizes and optimize our calculations. Inside findWinner, we create a nested helper class with the subtreeSize method, which calculates the size of a subtree recursively. If the size for a given order is already in the memo map, we simply return it. For new values, we compute the size using the same Fibonacci logic as before, store it in the map, and return it. After defining the helper class, we instantiate it and use it to calculate the total size of the Fibonacci tree for the given order n. This value represents the total number of nodes in the tree. We then initialize scores for Alice and Bob, which will track how many nodes each player claims during the game. To keep track of visited nodes, we create a Boolean array called visited, where each index corresponds to a node in the tree. Now, to simulate the game, we define a depth-first search function, DFS. This function takes the current node order and the current player's name as arguments. If the node order is invalid, meaning it's negative, or if the node has already been visited, the function simply returns. Otherwise, we mark the current node as visited and proceed to update the scores for the current player. This ensures that nodes are only visited once and that each player's score reflects the nodes they've claimed. The depth-first search function continues by exploring the left and right subtrees of the current node. For this, we recursively call DFS with the orders order 1 and order 2. The player's turn alternates with each recursive call, meaning if it's Alice's turn now, it will be Bob's turn in the recursive calls, and vice versa. Once the DFS simulation is complete, the game starts from the given node X, with Alice making the first move. After the DFS traversal is done, we compare the scores of Alice and Bob to determine the winner. If Alice's score is greater, the method returns Alice, otherwise, it returns Bob. This approach ensures that the game is fully simulated, and the winner is determined based on the rules of the subtree removal game and the structure of the Fibonacci tree. Here, we start with the Fibonacci tree of order 2, denoted as T2. Its structure consists of the root node 2, which has two children. The left child is node 1, and the right child is node 0. This gives the tree a total size of 3 nodes. For the game setup, we initialize some variables. The total size of the tree is 3, Alice and Bob both start with a score of 0, and a visited array of size 4, all initialized to 0, is used to track which nodes have been processed. Starting at node 2, Alice takes the first turn. The game begins with a depth-first search, or DFS, at node 2. During Alice's turn at this node, we mark it as visited and update the visited array to reflect this. Node 2 is now marked, indicating Alice has taken it. After marking node 2, Alice's score increases by 1, bringing her total to 1. From here, the DFS explores the left and right subtrees of node 2. First, it moves to the left child, node 1, where it becomes Bob's turn. At node 1, Bob marks the node as visited, updating the visited array accordingly. His score then increases by 1, and since node 1 has no children, the traversal of this subtree ends. Next, the DFS visits the right child of node 2, which is node 0. It is still Bob's turn, so he marks node 0 as visited. This updates the visited array once more, and Bob's score increases by 1 again, making his total score 2. Now, with no additional nodes to explore, the game concludes. Alice ends with a score of 1, while Bob has a score of 2, making Bob the winner of this example. Now, we move to the Fibonacci tree of order 3, or T3, which has 6 nodes in total. The structure of this tree is slightly larger. The root node is 3, with the left child being node 2 and the right child being node 1. Node 2 further branches into 2 children, node 1 on the left and node 0 on the right. On the other hand, node 1 has a single child, which is node 0. To begin the game, we once again initialize the game parameters. The total size of the tree is 6, the scores for both Alice and Bob are set to 0, and a visited array of size 7, initialized to 0, is prepared to track visited nodes. Alice takes the first turn, starting at node 3. During her turn at node 3, she marks it as visited, updating the visited array. Her score increases by 1, and the DFS proceeds to explore the left and right subtrees from node 3. The DFS first visits the left child of node 3, which is node 2, where it becomes Bob's turn. At node 2, Bob marks it as visited and updates the visited array. His score increases by 1, and he proceeds to explore the left and right children of node 2. The left child, node 1, is visited first, and it's Alice's turn again. Alice marks node 1 as visited, increasing her score to 2. Since node 1 has no children, this subtree is now complete. Next, the DFS moves to the right child of node 2, which is node 0, and it is still Alice's turn. Alice marks node 0 as visited, increasing her score to 3. At this point, the left subtree of node 3 is fully processed. The DFS then explores the right child of node 3, which is node 1, where it becomes Bob's turn again. Bob marks this node as visited, updating the array, and his score increases to 2. With no more nodes left to process, the game ends. Alice has a final score of 3, while Bob finishes with a score of 2. With Alice scoring 3 and Bob scoring 2, the result of this game is clear: Alice is the winner. For the next example, you can try applying the same process to the Fibonacci tree of order 4, where the tree structure and gameplay become even more interesting. The approach remains consistent: explore the tree using depth-first search, alternate turns between Alice and Bob, and keep track of scores and visited nodes. This iterative process will help you determine the winner just as we did in the previous examples. To analyze the time complexity of our solution, we start by breaking it into 2 main components. First, we have the calculation of the subtree size using the subtree_size function. This function employs memoization through row_cache to store results for each Fibonacci tree order. The recurrence relation for the size of a Fibonacci tree is based on the Fibonacci sequence. The size of a tree of order n is equal to the size of the trees of order n1 and n2, plus 1 additional node. Without memoization, this would result in an exponential time complexity of O2 to the power of n, due to repeated calculations. However, memoization ensures that each value from 0 to n is computed only once, reducing this step to O(n). Next, we consider the DFS traversal that simulates the subtree removal game. This traversal processes all the nodes in the tree, and the number of nodes is given by the Fibonacci sequence, denoted as Fn. Using the golden ratio formula, the size of the Fibonacci tree grows approximately as 1.618 (n/sqrt 5). These two components form the basis for analyzing the time complexity of our solution. Now, focusing on the DFS traversal, since it visits each node exactly once, the time complexity for this step is proportional to the size of the tree, which is denoted as f(n). Substituting the growth of f(n), this results in a time complexity of approximately 1.618 (n). Combining this with the subtree size calculation, the dominant term clearly comes from the DFS traversal. Therefore, the overall time complexity of our solution is 1.618 (n). Shifting to space complexity, we start by analyzing the memoization storage. The LeetCode cache stores results for every Fibonacci tree order from 0 to n, which means it requires n space. Additionally, the DFS call stack's depth corresponds to the height of the Fibonacci tree, which is equal to n due to the recursive structure of the tree. Thus, the maximum space used by the call stack is also n. Continuing with the space complexity, we also account for the visited array, which tracks whether each node in the Fibonacci tree has been visited. Since the number of nodes in the tree is n, the visited array requires n space. Substituting the growth of n, this becomes 1.618 (n). Considering all components together, the dominant term in space usage is the visited array, leading to an overall space complexity of 1.618 (n). Comparing this optimized solution to a brute force approach, we can see significant improvements. A brute force method without memoization would repeatedly compute the size of subtrees, resulting in an exponential time complexity of 2 to the power of n. By using memoization, we reduce the subtree size computation to n. However, the exponential growth of the Fibonacci tree size still dictates that the overall time complexity remains 1.618 (n). Similarly, the space complexity is dominated by the size of the visited array, making it 1.618 (n) as well. It's important to note that the time and space complexities are consistent across all cases, as they are determined solely by the size of the Fibonacci tree. Finally, we can validate these complexities with a mathematical understanding of the Fibonacci tree's growth. The size of a Fibonacci tree of order n directly corresponds to the Fibonacci sequence, which grows asymptotically as 1.618 (n/sqrt 5). This exponential growth is the primary factor behind the time and space complexities. The DFS traversal visits all n nodes, giving us a time complexity of n, which simplifies to 1.618 (n) when we substitute the growth rate of n. Similarly, the space usage is driven by the visited array, which also scales with the size of the tree, resulting in a space complexity of 1.618 (n). These results confirm that both time and space complexities are fundamentally tied to the exponential growth of the Fibonacci tree, completing our analysis. One common mistake when tackling the subtree removal game with a Fibonacci tree is misunderstanding the structure of the tree itself. Unlike a binary search tree or a balanced tree, the Fibonacci tree is defined recursively. The root node has two subtrees, the left subtree corresponds to Fibonacci, n1, and the right subtree corresponds to Fibonacci, n2. Misinterpreting this can lead to incorrect traversal strategies or subtree calculations. Another frequent pitfall is ignoring the game theory aspects of the problem. Remember, this is a competitive game where players alternate turns, each aiming to maximize their score while simultaneously minimizing their opponent's potential score. If you fail to account for the opponent's optimal moves, you could end up in a losing position. Inefficient recursive computations are another issue. If you calculate Fibonacci subtrees directly using recursion without memoization, you're likely to face exponential time complexity due to repeated computations. Dynamic programming or memoization is essential to optimize this. Lastly, watch out for incorrect score calculations. Some solutions focus only on maximizing the current player's score and neglect the impact on the opponent's score. A strong strategy always evaluates moves in terms of their overall effect on both players' outcomes. Overcomplicating base cases is another frequent error, especially for small Fibonacci trees, such as when n is less than or equal to 2. These cases should be simple and directly return pre-computed results instead of introducing unnecessary complexity. When it comes to interviews, it's essential to demonstrate a clear understanding of recursive structures. Be ready to explain how the Fibonacci tree is constructed and use this as an opportunity to showcase your recursive thinking. Game optimal strategies are another significant focus. You should highlight how to balance maximizing your score while minimizing your opponent's potential gain, and be prepared to discuss trade-offs between greedy approaches and dynamic programming strategies. Efficiency is also key, as interviewers may test your ability to optimize recursive solutions. Show that you understand how to implement memoization or even convert recursive solutions into iterative ones to improve performance. Lastly, be thorough in analyzing edge cases. For example, consider situations where n equals 0 or 1, and how your solution scales for larger inputs, such as n equals 20. Being able to address these scenarios demonstrates your ability to handle a variety of problem setups. The ideas and techniques used in the Subtree removal game appear in several related problems, making them excellent practice for refining your skills. For instance, LeetCode 877, the Stone Game, is another game theory challenge where players alternate turns to maximize their scores. It shares concepts like dynamic programming and optimal strategies. Similarly, LeetCode 1143, the longest common subsequence, highlights the importance of recursive thinking combined with memoization, which is directly applicable here. LeetCode 1312, minimum insertion steps to make a string palindrome, also involves recursive structures and dynamic programming approaches to solve a game-like optimization problem. Lastly, LeetCode 198, the house robber problem, is a classic example of solving overlapping subproblems efficiently using dynamic programming. The skills required to compute optimal scores in the Fibonacci tree game are directly transferable to these problems, making them valuable practice resources. Several approaches can be used to solve the subtree removal game, each with its strengths and trade-offs. A basic greedy approach might involve always removing the largest subtree available. While this is computationally fast and easy to implement, it often ignores the opponent's optimal responses, which can lead to suboptimal outcomes. A more robust method is dynamic programming with memoization, where intermediate results are saved to avoid redundant calculations. This approach is highly efficient but requires careful management of states, such as tracking whose turn it is and the current scores. The minimax algorithm is another powerful option. This game-theoretic method evaluates all possible moves and countermoves to determine the best overall strategy. While it provides accurate results, it can be computationally expensive unless combined with pruning techniques like alpha-beta pruning. Finally, iterative dynamic programming is an alternative that replaces recursion with an iterative process, often improving space complexity. However, this method can be harder to implement for problems that are naturally suited to recursive solutions. Each approach has its pros and cons, so understanding the problem constraints and requirements is key to selecting the most appropriate strategy. Great job following along. To recap, we analyzed the Fibonacci tree structure, explored strategic gameplay, and discussed key takeaways from this solution. Keep practicing similar problems to sharpen your skills, and don't forget to like and subscribe for more content. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!